3, 2, 1. Hi everyone. In this video we're going to be going over the lecture guide for Module 5. We're going to be talking about the first few vocab words and symbols, representative sample, bias sampling method, and a random sample. And then in another video we're going to go through example 1 together, just to kind of see what this looks like in an actual example. So this module is all about sampling. Well, what's sampling? You've already seen it. You've already dealt with, hey, here's a population. I want to know about this big population. So how do I learn about it? Well, I have some parameter that I calculate, right? The parameter, remember, is a way we measure something about the population. I want to know for this population the proportion, blah, blah, blah. I want to know for this population the average something, something, all right? But remember, that's almost impossible to do for pretty much everything we're ever going to want to look at. It's just not possible to do it. So I don't try to look at the entire population all at once. I instead grab a sample which comes from the population, right? This little circle I've grabbed from the population, but it's just smaller. It's something I can actually get my hands on. I then calculate or measure that same thing, but instead of the big group, I measure it for just the smaller one. And then I try to say, okay, I've got a number now. Is that number a good approximation for the big group, right? Our whole point here is, okay, I can't get this big number for this big group, right? Or I can't get this number for this big group, but I can get it for this small group, and that's going to be my best guess for what's going on here, the thing I actually want to know. So basically what we're doing is too much to do, find the parameter. Let's get the sample, let's get the statistic. That's our guess for the parameter. And what we'll do later in the course is we'll try to get an idea of how close we are when we do this work. And we'll actually be able to determine that. But all of the ability for us to do that is completely contingent on us getting a sample that's representative of the population. Big word here we got to be paying attention to. Representative. Big word, representative sample. So right up here, a representative sample. In order to do any of this work, in order for the statistic in here to really be a good guess for the parameter, so I'll say it again, in order for the statistic to be a good guess for the parameter, we've got to make sure our sample is representative of the population. So what does that mean? So in this little picture here, what I want you to pretend is the population is a big group of people. Okay? So in the bold here, there's a key word we have to look at. It says a sample should have the same characteristics as the population. Where did we see that word before? We saw that word when we were talking about variable. We said that a variable was some kind of recorded characteristic of an observational unit. Okay? So now let's think about representative samples in terms of variables. Here's my big population, big group of people. I have some variable. Let's make it categorical so the picture makes more sense. I've got some categorical variable, okay? Right? That I'm interested in asking each person in here about that. So here's what we're going to do. For that categorical variable, we've got options. Green, red, blue, black, purple, and this fun color, this fun mix of colors. So each person in the population, when I ask them this question, I try to go with this variable and I say, okay, what group do you fall into? Someone might say, okay, green. Someone might answer red, blue, and so on. Okay, so the variable and its options split up the population into these groups. This group would answer red to my question, this would answer green, purple, so on. Okay, so if I'm interested in learning about this population, right, then what I really need to do is I need to make sure my sample has similar representation of people who'd answer green, and then also a similar representation for people who would answer red and blue, and so on. I want to be a little more specific about what numbers, or how to think about this in numbers. When I look at my sample, right, maybe it's 100 people, and this one has 1,000, right? When I look at my sample, I want to make sure that the proportion of people who would answer green is about the same in this little group as it is in the big group. Okay, so well, what do you mean the proportion? So, see how in this big group, you've got this amount of green. This takes up some percentage of my big circle. If I have a representative sample, then when I shrink my circle down, because that's what a sample is, right? It's taking your big population and shrinking it down smaller. When I take this big circle and shrink it to the small one, I want the percentage of green to stay the same. So I want the same percent of people who would say green in here as in here. Not the same number. I don't want the same number because you're getting smaller, so your number of people who would say green should get smaller. I want the same percentage. So you might ask, okay, what's an example of this? And so the elections are coming up. You're going to see lots of polls, election polls. These are all just surveys that have been sent out to likely voters or some group of people who we think are going to vote. And what we ask them is a bunch of information, a bunch of characteristics about them. To start, we ask usually gender, race, we ask age group. Many times we'll ask what political party, if any, do you align with. And so what we're interested in is every time we take a sample, we want to make sure that the proportion of people, this is important, the proportion or percent of people in our sample who are age 50 plus, or who are men, or who are Democrats, or who are Republicans, or who are yada yada yada. We want to make sure that the proportion or percent of the people in our sample who are any of those things matches the proportion or percent of the population who are those things. Okay? So just think about this. Just pick out one. Let's just pick out age, right? Let's say, and we're making these numbers up, let's say 30% of your population are over the age of 50. So we're just going to make it up. Let's just say 30% of the population's over the age of 50. So you're interested in asking a question about everyone. So you take a sample, and you get to the sample, and you look at your sample, and you realize, wait, 70% of this sample is over the age of 50. And you try to ask them a question, you get some data, you get a statistic, and you go back and you look, and you say, okay, I got a statistic. This is my guess for the parameter. But is it? Is it a good one? You oversampled people over the age of 50. Your sample does not represent your population, right? You are not giving an equal chance to get information from those under 50 because you oversampled over 50. So if your sample is not representative of your population, then your statistic could possibly be quite far off your parameter. If people over the age of 50 would answer your question, whatever you're interested in, would answer your question differently than people under the age of 50, then your statistic will show that, and it will be either larger or smaller, significantly many times, bigger or smaller than your actual parameter. And you'll have no way to know. So we can't let that happen when we're trying to do statistics. Now, that's very difficult because taking a random sample, which is what we need to do, is also very difficult. And so there's lots of ways to try to balance this and try to balance the groups and make sure you're getting the right proportion of age groups, the right proportion of every other thing you could think of. And we'll talk later in the course about how difficult that is too. But the ultimate goal would be to try to represent every possible group in your sample for every possible variable. That's the tricky thing. It's not just that you want to make sure all the age groups are represented. You also want to try to make sure that if you now take this population and split along race, or split along political party, or split along blah blah, all these other ones, you also want to make sure that you've represented with those variables too. And so I want you to think about that. How hard does it sound to try to do that by hand? If you could even know from your population the percentage of people who are old, young, Democrat, Republican, independent, whatever, it would be very difficult to first get that information. And then second, even if you did, it would be very difficult to take them, all your population, and only grab certain people so that you were trying to make sure you had the right proportions of each of those variables. It's so difficult. And so it sounds at this point maybe like, well, this is impossible. How do I get a representative sample if this is so difficult? The way we do it is called random sampling. So we are going to take, in this class, simple random samples. What does that mean? It means I'm going to take your population of voters. I'm going to put their names down on pieces of paper. I'm going to toss them into a giant hat, shake it all up, and pick names out. Pick out name. And the idea being, if I shuffle good enough, then when I pick a name out, it's equivalent to just randomly picking a name. We're not actually going to do it like that, but for a visual, that's something you can do. Put the names in a hat, shuffle them all up, pick a name out without looking. If we do this simple random sampling, then what we do is we end up giving everyone in the population an equal chance of being picked. So that's awesome. That's what we want. We want to be able to give everyone an equal chance, right? Because that would mean that this purple proportion here, the people who fall into this purple group, we should end up in the sample with about that same percentage or proportion in the sample of people who fall into the purple group. Now this is random, so it's not going to be perfect, right? Randomness means it's not going to be perfect, but it will be good. It will be pretty good. It will do a good job. So, simple random sample. We go, all right, population, close my eyes and just randomly grab you, put you into the sample, find my statistic. Now I feel pretty good that my statistic will be close to this parameter. We haven't talked about how close. We'll talk about that later. But if you randomly sample, you should feel fairly confident that your statistic is a good approximation of the parameter. So we need to put a name on something. And what we're going to do is we are going to put the name sampling bias on us being wrong or doing something wrong about sampling. So what do I mean by that? Well, let's look at the definition. A sampling method, so what does that mean? All this means is how you pick your sample. So just take this away and throw in how I pick my sample. That procedure you use, the way you pick, we will call that biased if it produces sample statistics that are consistently overestimating or underestimating the parameter. So if you design a method, just go talk to the next 10 people that I talk to, and if that leads you, once you've gathered your data and got your statistic, if that leads you to having a statistic that is bigger than the parameter or smaller than the parameter, and every time you do your method again, like, okay, I'm going to just go talk to another 10 people again. I'm going to do it again. Okay, again, my statistic is bigger. I'm going to do it again. Okay, again, my statistic's bigger. Right? I'm looking at height, and I'm sitting at a basketball game, and I keep just talking to the players. Each new team, I'm like, oh, I'm going to get your height again. Well, clearly, that's bad, and I'm going to end up with average heights that are much taller than the average person's height, which is, for some reason, what you were interested in, maybe. So if you have a method that when you apply that method to get your sample, just to get it, if you apply that method to get your sample, and every time you do that, your statistic keeps going, keeps being too big, or too small, we're going to call that biased. So sampling bias comes in when you take a sample in such a way that your statistic over, bigger, that just means bigger, or underestimates, smaller, the actual parameter. So you're going to see that in the weekly activity. When you go to do that, be paying attention, right? Be paying attention for the sampling bias. There's a question on it, but pay attention to it. Okay, so in the next video, we will go over example 1.